Okay, na? Right. So in your last class, we discussed introduction part of photochemistry, where we discussed about how photochemical and thermal reactions are get differentiated. Then we discussed what is the importance of photochemistry. Then we also discussed what are the sources, then activation and deactivation. So there we discussed how to make deactivation of a excited partner. Then types of molecular energy starting from translational, rotational, vibration and electronic energy levels. At last we learn what is thermal reaction, photochemical and differences between them. Then finally we discussed what are molecular orbitals, what are gyrated and what is ungyrated. Okay, so next one, after molecular orbital, electronic transitions. Electronic transitions. Next is electronic transitions. So what is the meaning of electronic transition? Electronic transition nothing but C, promotion of electron from ground state to excited state. Promotion of electron from ground state to excited state is called electronic transition. So means we are promoting one electron from ground state to excited state by irradiating with light. Which means if I take this is a ground state and this is I am assuming as excited state. Two electrons are present here. Now by irradiating with light, then what happens? See, this electron migrates from here to here, or this electron jumps from here to here. That is called electronic transition. So generally electronic transition takes place from. So from where it will observe? In most of the cases, electronic transitions takes place from BMO to ABMO, and one more is non-bonding molecular orbital to ABMO. Only these two possible electronic transitions are possible. ABMO to ABMO not possible, BMO to NBMO is not possible. So which means if I take any bonding molecular orbital and this is anti-bonding molecular orbital, electronic transition possible. This is energy order. And if I take non-bonding molecular orbital, anti-bonding molecular orbital, electronic transition is possible. Electronic transition possible from BMO to ABMO, lower energy to higher energy, non-bonding to ABMO, but not from a corresponding BMO to NBMO. BMO to NBMO not possible. BMO is lower energy, NBMO is high energy. But BMO to NBMO electronic transition is not possible. Only two possible electronic transitions are expected. That is ABMO from BMO, now ABMO from generally NBMO. Only these two are possible. So BMO to non-bonding molecular orbital electronic transition is not exist. Okay. Next, in that first one, types of electronic transitions. What are the types of electronic transitions are there? Types of electronic transition. First I am taking ethane. So ethane carry only sigma bonds or not? Only sigma bonds are present. Ethane carry only sigma bond. That's why I can write sigma and sigma star. Only one possible electronic transition possible. What is it? Sigma to sigma star. Ethane give only one electronic transition. Suppose if I take ethene, this is ethene, carbon-carbon double bond I am writing. Now see, here there is a presence of sigma and pi. When sigma pi both are present, so on that time sigma, here sigma star, here pi and here one more pi star. Total 4 possibilities are expected. Sigma to sigma star, sigma to pi star, sigma to C. This is sigma. Sigma to sigma star, sigma to pi star, pi to sigma star, pi to pi star. Total 4. So they will give 4 possibilities. Sigma to sigma star, sigma to pi star, then what is one more? pi 2 pi star, pi 2 sigma star, total 4. Ethane have a tendency to give 4 electronic transition. Ethane having only sigma bond, they will give only sigma to sigma star. Okay, and if I take any carbonyl group, carbonyl having a lone pair of electron or not? See, there is a lone pair of electron. Now I can write sigma pi non-bonding like this. Sigma pi, this is non-bonding. Pi star, and what is one more? Sigma star. Now sigma to sigma star, sigma to pi star, then followed by pi to sigma star, then pi to pi star, n to sigma star, n to pi star. Total how many? 6 are possible. So only these two are possible. Out of these two, based on molecule, overall maximum 6 possible. So that 6 possibilities are sigma to sigma star, sigma to pi star, pi to pi star, pi to sigma star, then followed by n to sigma star, and what is one more? N to pi star. Depends upon molecule, that may changes. Okay, but maximum transition exhibited by any organic molecule is 6. Out of these 6, so generally see, only 2 transitions are not exist. 100% 2 transitions are not exist in all cases. What are they? N sigma to pi star not exist, and one more is pi to sigma star not exist. Everywhere these 2 transitions are not possible. Sigma to pi star, one more is pi to sigma star, these 2 are not exist. In this only 2 are possible, in this only 4 is possible. Because due to symmetry. If any higher molecular orbital and lower molecular orbital having same symmetry, electronic transition is not exhibit between them. Suppose if you want to make any electronic transition, so definitely there is a possibility of exhibiting gerade and ungerade. Gerade to ungerade transition possible. Ungerade to gerade electronic transition possible. But gerade to gerade, ungerade to ungerade electronic transition not possible. If any 2 molecular orbitals having same symmetry elements, electronic transition is not exist. Suppose both having plane of symmetry not exist, both having center of symmetry not exist. So one having center of symmetry, other having absence of center of symmetry, then electronic transition possible. So what is the meaning of gerade? Presence of center of symmetry. Ungerade means absence of center of symmetry. Now this molecular orbital having center of symmetry and they don't have center of symmetry, that's why electronic transition possible from sigma to sigma star. And even from pi to pi star also possible. Because pi is a ungerade, what about pi star? It is gerade. Pi to pi star possible. So see, gerade is there. Sigma to pi star, what is it? Gerade. So that's why sigma to pi star not exist. And one more, ungerade to ungerade. Pi to sigma star also not exist. And one more, if you take carbonyl compound exhibits only 2. Most famous electronic transition for carbonyl compound is pi to pi star, one more is n to pi star. Remaining 4, out of the 6, only 2 are exist for carbonyl compound. One is n to pi star, other is pi to pi star. Remaining all are not exist due to energy and symmetry criteria. It is high energy transition. Sigma to sigma star, n to sigma star is high energy. That much amount of energy we are not providing. That's why due to insufficient energy, due to presence of symmetry, 4 electronic transitions are not possible for carbonyl, only 2 are possible. What are they? N to pi star, one more is pi to pi star. Okay, these are the overall 6 possible electronic transitions, and especially for carbonyl compound only 2 are really possible. N to pi star, pi to pi star. Right. You take directly. So alkane give how many electronic transition? Only one. Alkene give how many electronic transition? Only, how many are possible? Only two. Possibility are 4, but real only 2. 4 are possible, but real is only sigma to sigma star, pi to sigma star, pi to pi star. Remaining 2 are not exist due to symmetry. If two molecular orbitals having identical symmetry element, electronic transition between the two energy levels is not exist. So, see, in carbonyl compounds, possible number of electronic transitions are how many? Possible number of electronic transitions are 6. Possible number of electronic transitions are 6. But in spectrum produce only 2 electronic transition. Produce 2 electronic transition. So what is the reason? Due to symmetry and energy criteria. Symmetry and energy criteria. Insufficient energy, symmetry. So due to these two reasons, all transitions are not exist. So energy, symmetry, what is symmetry? Sigma to pi star. Second one, pi to sigma star. These two are belongs to symmetry criteria. Due to presence of identical symmetry, electronic transition not possible. And second case, so sigma to sigma star, third one, n to sigma star. So they required high energy. High energy transition is required. That much amount we are not providing. So these two not exist. Only 2 more transitions are possible. This is third one and this is fourth one. See, only 2 are possible. Pi to pi star, that is n to pi star. Only these 2 are exhibited by carbonyl. This is not possible due to symmetry because this is gerade. And what about here? Gerade. This is ungerade, ungerade. So gerade to gerade not possible. Ungerade to ungerade also not possible. If 2 molecular orbitals having identical symmetry, electronic transition not exist. Suppose if 2 having plane of symmetry, no transition. 2 having center of symmetry, no transition. One should have center of symmetry, one should not have center of symmetry, then only electronic transition possible. This is concept related to UV. Here only I am explaining. Okay. Suppose if you consider sigma, sigma star, and if you consider pi, pi star. Now is it sigma to sigma star possible? Yes. Pi to pi star possible? Yes. Is it sigma to pi star possible? No. This is not possible. It is same way pi to sigma star is also not possible because it is gerade, ungerade. This is ungerade and what is this? Gerade. Gerade to ungerade possible, ungerade to gerade possible, but ungerade to ungerade, gerade to gerade not possible. Only one key point you need to remember. Electronic transition between 2 MOs possible only when the 2 having different symmetries, otherwise both having unequal symmetry elements. One having presence of symmetry, other having absence of that constant symmetry. Then only electronic transition is possible. This is key point in UV. So which among the following electronic transition not possible? Means what you will say? Which is not possible? Sigma to pi star, pi to sigma star not possible. Remaining all are possible. See, it is also possible. Sigma to sigma star, n to sigma star possible in carbonyl. But what I am saying is, we are not providing that much of lambda. Means that amount of energy we are not providing. That's why in maximum cases carbonyl, these 2 transitions would not consider. We are not considering. Possible, but we are not considering because we are not providing sufficient amount of energy. Due to less amount of energy, this is not exist for carbonyl. Due to absence of the identical symmetry. Okay, then this is also not possible. Only one possibility is expected from pi and n. Only this set of transitions are possible for carbonyl compound only. So after types of electronic transition, then followed by multiplicity. Multiplicity, it is represented by J. Multiplicity. This will also helps in UV. Be careful. That is the advantage of photochemistry. Whatever basics are there in UV, that I will cover in photochemistry itself. Two advantages is there. Photochemistry and UV. And in your examination, maximum UV questions are not asking. Because there is a link with photochemistry and UV. Suppose if they want to ask any UV question, they will ask directly lambda max. Okay, chromophore question, otherwise oxochrome, hypsochromic shift, hyper, like that. Some selective areas will be there, but there is not that much important area for asking any question in CSR. Okay, but maximum they will ask either lambda, otherwise link with photochemistry and UV, absorption bands. See, orientation of electron and their spin at excited state is multiplicity. Multiplicity is nothing but what is the orientation of electron, how electron is orienting, and what is the spin of that electron. That is called multiplicity. So how multiplicity is represented? J is equal to formula 2s plus 1. J is nothing but multiplicity. S is equal to spins of electrons. Electron spins. What is multiplicity? How excited molecule electrons are orienting. In excited molecule, how electrons are orienting, what is the spin of that electrons? That is called multiplicity. Okay? Generally, if I take any excited state molecule exhibits two types of multiplicities. Excited molecule exhibit two types of multiplicities. So what is it? Singlet, second one. First one is singlet. First one singlet, second one is triplet. Two types of multiplicities will be there for excited molecule. Which means when any ground state molecule, this is ground state, S0, otherwise we can say this one, S0. Now photochemically it is irradiated. When photochemically if you irradiate, now this molecule becomes excited. Okay? This is called excited molecule. So this excited molecule having two types of multiplicities. Excited molecule having two types of multiplicities. First multiplicity, excited molecule with same electron spin with respect to ground state. That is called opposite electron spin. This spin almost all same. And one more is there, excited molecule having a same parallel spin. If excited molecule having opposite spin, this is called singlet. This is singlet, and what about this one? This is called triplet. So how many multiplicities are expected for excited molecule? Two multiplicities. Singlet excited state, one more is triplet excited state. Singlet excited state having opposite spin of electron. Triplet excited state having same spin of electron. See, clockwise, what about here? Clockwise and anti-clockwise. So what is the spin state of this one? It is also clockwise, anti-clockwise. This is excited molecule. Okay? So when if it is excited, two possibilities will come. So that's why I see this may retains as it is, this may give this one. So that's why better don't write these two possibilities here. You better write this is activated molecule. You may get activated singlet, activated triplet. From here onwards be careful. Because slowly we are entering into Jablonski diagram, Frank-Condon principle, Hund's rule of maximum multiplicity. So most important concepts are going to come, which will help in UV as well as interconversions in photooxidation, reduction, etc. Okay, it is a ground state molecule. Photochemically I am irradiating, it is getting excited. We know excited molecule having two multiplicities: singlet multiplicity with opposite spin electron, triplet multiplicity with same spin of electrons. Okay, right. Singlet nothing but 1, triplet nothing but 3. So here see, excited state molecule having opposite spin of electrons, that is known as singlet. This is singlet multiplicity. Now same, excited state molecule having same spin of electrons, that is known as triplet. Excited state molecule having opposite spin is opposite, clockwise, anti-clockwise, and excited molecule having same spin, clockwise or anti-clockwise, that is called triplet. So here this is a ground state molecule. This is M, otherwise we can say S0, ground state. Now this is photochemically accelerating now. Photochemically I am accelerating. So when it is photochemically accelerated, two possibilities are expected. Ground state molecule accepting this, now it is activated in two ways. One, in first case what happens, see, this is clockwise, this electron is as it is. Now it is anti-clockwise or not? Anti-clockwise. What is the state of this electron? Anti-clockwise. After excitation, what about this? Anti-clockwise. So now this state is called singlet state. This is singlet state. Here M star represented by clockwise, anti-clockwise. It is clockwise, anti-clockwise, still it is clockwise, anti-clockwise. This electron is migrating from lower energy level to higher energy level with same spin, anti-clockwise, but after excitation anti-clockwise only. Okay, now here see, same energy level I am writing, here it is clockwise, now it is clockwise. What is the spin of this electron? Anti-clockwise. Now it is spins to opposite, it will goes to opposite side. Now this is called triplet. This is triplet, it is excited and having clockwise and clockwise. And apply 2s1 formula for this one. 2s plus 1. J is equal to 2s plus 1. So what about S here? Spin of electron. Clockwise, anti-clockwise. So clockwise plus of, anti-clockwise minus of. So sum of these two electrons are 0. So here finally 1. That's why it is called singlet. Suppose here see, if you apply J is equal to 2s plus 1 formula. So 2 is equal to plus of 1. Here plus 1. 2 plus 1 how much? 3. That's why it is called triplet. So two possibilities we are learning. Photochemically triplet, photochemically singlet. So whatever multiplicity is there for ground state. What is the multiplicity of ground state? This is singlet multiplicity. And what is the multiplicity of this one? Singlet. This is called retaining their multiplicity. This is called S0 and this is called S1. This is S0, S1. And what about here? This is called T1. So ground state multiplicity retains ground state multiplicity retains in S1 state. S1, S2, S3, S4 all are retaining their multiplicity. What is the meaning of retaining multiplicity? Singlet to singlet, triplet to triplet. But what happens? See, ground state to triplet. This is inverting their multiplicity. Any molecule when excited, they should retain their multiplicity. They should not invert their multiplicity. Inverting multiplicity always not exist. That transition not exist. If any molecule is exciting, how many possibilities are expected? Singlet, triplet. Singlet to singlet possible. Triplet to triplet also possible. But singlet to triplet not possible because symmetry. So here singlet multiplicity is there, singlet multiplicity retaining. So molecular orbital, whichever multiplicity is there, if they retain their multiplicity, the transition is allowed. If they are inverting their multiplicity, transition is forbidden. When electron is absorbing energy, if it is excited, retaining same spin. Here what is the spin of this electron? Anti-clockwise. What is the spin of this electron? Anti-clockwise. See, what about this electron? Clockwise. What is this? Anti-clockwise. After absorbing energy, that electron goes to higher energy level and becomes a anti-clockwise. Is it initially anti-clockwise? But finally after excitation still anti-clockwise. Only that transition is possible. Initially anti-clockwise. After consuming energy, excites and anti-clockwise only. Suppose initially anti-clockwise, after excitation if it is rotate clockwise, that is not possible. That transition is not possible. Retention of spin, retaining multiplicity is allowed transition. See, what is the spin of this one? Anti-clockwise. After excitation, what is the spin of this electron? Anti-clockwise. That transition is possible. What is the multiplicity of this state? Singlet. What is the multiplicity of this state? That transition possible. So what is the spin of this electron? Anti-clockwise. But right now see, clockwise. This is impossible. We can't create directly. When any electron absorbing energy, it will undergo excited, and once if it is excited, their spin never changes. Generally in your books they will write opposite spin. In fast they will write, but that is not correct. 100% is not correct. So don't think that before clockwise, after excitation anti-clockwise, that is wrong. Initially anti-clockwise, after excitation also anti-clockwise, only energy changes. So here no energy, now energy increases. So retaining spin possible, retaining multiplicity is possible. Inverting spin not possible, inverting their multiplicity also not possible. Clear? Right. Clear? So this is a formula to calculate multiplicity. Singlet multiplicity 1, triplet multiplicity 3. Suppose if I take any molecule, see this molecule is in ground state. So ground state molecule having S0 or not? Ground state molecule having S0. So when ground state molecule having S0, it will give S1, then it will give S2, then it will give S3, regularly it will give S6. Right? What is S0? Ground state multiplicity. Ground state multiplicity. First excited singlet, second excited singlet, third excited singlet, xth excited singlet. Now later on what happens, see, S0 next year followed by T1, then T2, then T3, and here followed by Tx. Don't write arrow like this, it is impossible. When any molecule absorbs energy directly from S0 to S1 possible, S1 to S2 possible, S2 to S3, like that it is possible, but S0 never give T1. Why it is not possible to give? Inverse their multiplicity. See, singlet converted to triplet, possible? No. Singlet to singlet possible. Singlet to singlet possible. Okay, so it is singlet, it is also singlet. That's why this direction only always any molecule is excited. Only this direction it will excite, not this direction. It is indirect direction, not possible directly. This is possible only with photosensitization. New concept is going to come, photosensitization. Okay, be prepared. If any molecule is absorbing energy, they will excite by retaining their multiplicity. They will jump and they will retain their multiplicity. Singlet to singlet, triplet to triplet, but singlet never give triplet, triplet never give singlet. Only excitation I am saying. So ground state multiplicity retains in excited state. Here it is not retaining, that's why it is forbidden, not possible. But here it is possible, so that's why this is first excited, second, third, fourth. Now first triplet state, second triplet state, third triplet state, etc. Okay, so here I am writing 1 point C, lifetime of Sx is minus 31 second. Next, lifetime of S1 minus 10 to the power of 8 second. Then one more, lifetime of T1 10 to the power of minus 3 second. It is a lifetime. What is the use of lifetime? More lifetime means what? What is the meaning of lifetime? What is your lifetime? Maximum 100 years, round number, round figure. Finally you decided that 100 years is round figure. Possible? Nowadays impossible. Maximum 60 or 65. Okay? And even that too, you will suffer with many diseases. Finally you will get an output after 65. Right or not? Hardly. If you take hygienic food and proper exercise and mental if you are strong, then you will be healthy up to 30 years or 35. Once if you cross 35, from there onwards, diseases will be get increases. Finally you will get a ultimate result after 65. But don't expect round numbers 100, 150, 200 like that. So if you possible, but you need to maintain proper diet. Proper diet, mentally strong, physically strong. Then possible, you can live maximum 100 years. So in olden days they are saying that you can live blessed for 100 years. Everywhere if you ask them, blessed for 100 years. But right now, blessed for 60 years without any diseases. Right or not? What is the use? You are living for 100 years, you are continuously suffering from many diseases. What is the use? No use. Right? You are living for 45 years without any disease, that is ultimately good. You will be not a problem for any other people. You require support. So that's why living with diseases 100 years no use. Living without diseases 30 years is better. So that's why first you are a chemist, so that's why you are learning chemistry, that's why you become a chemist finally. You need to suggest proper food for many people. Okay, don't eat whatever is appeared in front of you. Right or not? Try to intake which is good for you. Good for you means what your body asking, not your tongue asking. Right or not? What your body asking? Your body asking only energy. It is asking only, you provide energy, I will work conveniently for you. But what you are providing? Whichever appear in front of you, which is good for tongue and which is good in taste, only that you are intaking. Forget about inside what is going on. Okay? So, if you take better, animals are better as compared to humans. So if you take any goat, provide some meat, whether they will eat. Take a goat or any sheep, provide some meat. It will smell, they won't eat. Why? Why it is not eating? Suppose take any lion or tiger, provide some grass continuously. After 1 week, it is not eating. You are not providing meat for that. After 1 week, you are providing some grass. Whether lion or tiger will eat grass after 1 week without providing food? No. Why? Still hungry is there. Hungry is there, but that animal is not eating grass. Same goat. Don't give anything for 1 week. Provide continuously water. After 1 week, provide some meat. Whether they will eat that meat, even though it is hungry? No. Take a human being. Take a human being, provide only water for 1 week. After 1 week, whatever you provide, they will eat. Right or not? We are eating grass and we are eating veg and non-veg, everything we are eating. Right? That's why we are suffering from all kinds of diseases. Any animal suffering from sugar? Any animal? Any animal not suffering from BP? No thyroid? Nothing. These are the top diseases in India, top diseases in anywhere. BP, sugar, thyroid. Right? Why? Not any animal, any dog is not suffering from BP. They never went for any hospital to diagnose. Right or not? No BP, no sugar, nothing. Happily they are running, happily they are eating whatever they want. But they know which food is designed for their body. So that's why they are not facing any kind of problem. So what is our food? Like that, our body also one food is there. That food we are not eating regularly. What is that food? Fruits. Our food is only fruits. If you intake only fruits, you will not suffer any kind of diseases. 3 times a day, nothing will happen. But starting little bit problem, but once if your body supported, so if you intake all fruits by ignoring remaining all things, 100% you will not get any kind of diseases. Even if you have a disease, that will be completely cured by intaking fruits. So even at least 1 month we are not going to eat one fruit, clearly. 15 days or hardly 10 days, sometimes we will forget to eat some fruits also for many days even. So that's why our food is not rice, our food is not chapati, our food is not idli, dosha. These all are not our foods. That all are artificially intaking food for taste purpose only. Ultimate thing is we want taste. Here if they given signal, automatically input will be there. We don't want what it will do in inside. Right or not? If taste is good, then we will give good input for our body. So that's why, see, if you want to live without any disease or without any health issues, try to intake maximum fruits. If you intake fruits, automatically your diseases will be, your body itself it is going to cure. Not going to take any external medicines. See, body suffering from any health issue, you are intaking any medicine to cure them. And if you take any roadside animals, so even if they fight with each other, so even though they get any wounds on their body, itself it is going to be cured without any medicine. Because they know which kind of food is responsible to increase their immunity. So whatever food we are taking, that is not improving our immunity so that it can be diagnosed. So that is a major problem. Take down here. It is a lifetime nothing but how much time it will settle down on SX state. The time spent by any electron in S1 state. The time spent by any electron in T1 state. Out of these 3, at which particular state lifetime is very high? T1. It is very fast it will moving. minus 31 means lifetime is very less. Suppose if I write plus 31, very high lifetime. Minus 31 means 10 to the power of minus 31 means lifetime is very less. So out of T1 S1. So this T1 S1 having a maximum lifetime. Out of S1 T1 having a more lifetime. As lifetime increases, stability increases, relaxation increases, time spending on corresponding molecular orbital increases. When time spending increases, automatically chemical reactions also possible. So see, if you are not spending much more time means no proper result. Your lifetime is very less. Within seconds it is coming back to ground state. Now it is spending little bit more time. It is spending more and more time. If lifetime increases, if you spend more time, then chemical reactions also very high and effective reactions. That's why as compared to singlet and triplet reactions will give excellent yield as compared to singlet. What is the key reason for triplet reactions? Because triplet reactions will give high lifetime. But is it T1 possible? Ground state molecule, whenever if it is excited, which is possible? S1 possible. Is it T1 possible? No. But T1 is giving a good result. But T1 is impossible to prepare. Once if you prepare T1 over, you will get an excellent reaction. Okay, be prepared. Our target is S1 and T1. Between S1 and T1, S1 having a less lifetime, T1 having a more lifetime. As lifetime increases, there is a sufficient time for reactant to participate in chemical reaction. So they will give proper yield. Okay, suppose if you are writing examination, 3 hours examination time is there. But I am saying that I am going to give only half an hour. Will you write? No. I am saying that I am giving only 15 minutes. Will you write? Actual exam time is what? 3 hours. I am saying that try to complete examination within half an hour. That is S1. Okay? Now, I am saying that try to complete exam within 1 hour. That is T1. Between T1 S1, which is having high time? T1. S1 having less time. S1 30 minutes. T1 how much? 1 hour. Then go for one more. SX. I am saying that try to complete exam within 1 minute. Possible? So that is SX. So, which is better? Either S1, T1 or SX? T1. But T1 generation is not easy. T1 is not possible to generate. Why? See, S not responsible to S1. S1 to S2, S3, S4 it is possible. But is it possible to generate T1? No. So that's why singlet chemical reactions are different, triplet chemical reactions are different. Ground state reactions are different. That is thermal reaction. Excited state, 2 reactions are there. Excited singlet, excited triplet. Excited singlet, many reactions are possible. S1 reaction, different product. S2 different product. S3 different product. Every excited state having a different product. It is same way every excited triplet also having different product. Whichever state having a more lifetime, that will give excellent yield. Okay? So out of all possible electronic excited state, which state having more lifetime? T1. T1 will give excellent product. But generating T1 from S0 is possible? No. Other alternative is there. I will show that alternative. How to generate T1. Okay, next is Jablonski diagram. There you will understand how to generate T1. After Jablonski, we will see photosensitization. Clear? Right. So what is the relation for lifetime for excited state and chemical reaction? What is the relation between lifetime of excited state and chemical reaction? More lifetime, more amount of yield for that particular reaction. If you spend more time in examination hall, then only you will get good result. You need to write. First of all, you need to write. Don't think that, sir, I want to spend 3 hours, but I don't want to write means. That is not the case. You need to spend time and you need to write. Spending time means you are writing. Here also, spending time means it is reacting. We need to give time for reactant after excitation, sufficient time responsible to give product. It is ready to participate, but we are not giving time. You are prepared very well for examination. You can write total paper, but I am not giving time. That is called SX state. Even S1 state also. One more state is there, T1. Out of these 3 states, which is the better state for participating chemical reaction? T1. But T1 generation is not easy. That point you remember. T1 is giving excellent yield. T1 state can give excellent yield, but generating T1 is not the easiest task. Okay, that's why a new concept is going to be introduced, photosensitization. Photosensitization is a concept which is required to generate T1 state for a molecule. Is this molecule give T1? No, but photosensitization is a process which can generate T1 state for this molecule. From T1 state, more amount of yield, different product. Don't think that, see, S1 will give one product, T1 will give different product. S1 product, T1 product is not same. S1 product is different, T1 product is different. And S1 yield is different, T1 yield is different. S1 yield is always less, T1 yield is always high. Clear? Right. Next, third one in that case, Hund's maximum multiplicity rule. This just now I explained, Hund's rule of maximum multiplicity, otherwise Hund's maximum multiplicity rule, both are same. Hund's rule of maximum multiplicity. Hund's maximum multiplicity rule. See, every excited molecule having two possible states, singlet and triplet. Every excited molecule having two possible states, singlet and triplet. So according to this rule, excited state having maximum multiplicity, excited state having maximum multiplicity found to be stable. According to this rule, excited state having maximum multiplicity found to be stable and provide high amount of yield. Hund's rule is saying that, Hund's rule of maximum multiplicity is really saying that every excited state molecule having two possible states, singlet and triplet. This rule is saying that whichever excited state having more multiplicity, that state is found to be more stable. And from that state, you will get more amount of yield if they participate in chemical reaction. So which state will give more amount of yield? Triplet. Right or not? So this is actually Hund's rule of maximum multiplicity rule. This is S0, this is S1, I can say S2, this is S3, like that. It is keep on progress like this. So here you will expect S6, like that. Regularly it is keep on progressing. And every singlet having a T1, and here T2, and here T3. So it will progress like this, and here you will get, this is Tx. every excited having singlet S1 T1, S2 T2, S3 T3 like that. This rule is saying that when electron excites from S0 always goes to S1 only. They never give T1. Directly from here to here it is not possible. It is impossible, remember. S0 to T1 not possible. S0 to S1, S0 to S2 possible, S0 to S3, it is go like this because same spins. So every excited state having two possible excited states, S1 T1, S2 also having T2, S3 also having T3. So the energy of singlet is very high as compared to energy of T1. Energy I am saying. The energy of Sx is greater than energy of Tx. Then what about stability? Stability order finally. Stability of Tx is greater than Sx. Then finally I can say that stability of T1 is a little bit better as compared to T1. That is your final conclusion. This is energy and this is stability. That is called Hund's rule of maximum multiplicity. Only one point you remember. This is saying that when electron is excited, every excited partner, whichever excited state having more multiplicity, this is more stable. This is more stable as compared to this he was saying. What is the multiplicity? 3. What is the multiplicity? 1. But what we are saying is, even though T1 is more stable, even though T1 is adjacent to S1, but T1 preparation is not possible directly from S0. Clear? What is our target? Our target is to prepare T1. Is it T1 possible directly? No. S0 to S1 possible. S0 to S2 possible. Like this higher energy possible, not from T1. It is found to be stable and that will provide more amount of yield or high amount of yield. So yield point of view, if you consider triplet having more amount of yield if they participate in excited state as compared to S1. So out of this all excited state, which is having more lifetime? Out of this all, T1. Which is having less lifetime? Which is having less lifetime? Sx. Next, Tx. Sx having less lifetime, later on Tx. Every singlet adjacent triplet is there. Every excited singlet adjacent triplet is there. Allowed and forbidden transitions. Allowed and forbidden transitions in photochemistry and UV. Allowed and forbidden. Clear? Right. See what is allowed? high probable electronic transition in a molecule is allowed. High probable electronic transition in a molecule is allowed. That is the meaning of allowed. Means it is the most possible electronic transition. That is called meaning of allowed. Okay. So we can also define in one more way. The transition in a molecule, takes readily in UV visible range with high intensity is allowed transition. So that is the meaning of allowed transition. Allowed transition nothing but the transition which is more favorable in molecule, the transition which takes place readily, the transition which will give more intensity, that is called allowed. So whichever is allowed, whose absorption maximum is 10 to the power of 4. This question given in DL exam. What is the meaning of allowed transition? Allowed means it is a one kind of transition in a molecule which will take very faster, which will give more intensity, which will not take any time, which will take in a short time and it will give more intensity. That is the meaning of allowed. Allowed nothing but highly possible transition is called allowed. Okay, everyone will respond, but whichever transition respond very fastly every time, that is called allowed. So 4 children are there in family. Okay, so when mother is shouting in house, mother is calling, all people are watching TV blindly. They are opening their mouth or they are continuously eating and they are watching TV. Okay, mother is cooking in house, inside. He was shouting. No one is responding. Only one person every time he will respond. Out of 4 children, one person always they keep one of their ear towards their mother. When mother calls, only one person, elder brother, he was responding every time. He was allowed. Remaining three, they will respond very slowly. If this person is running, then he will say like this. Means they are called forbidden. Okay? Forbidden means don't think it is not possible. Forbidden means late response. Delay, very slow, dead slow. Okay? So generally you people think that forbidden means not possible. No, forbidden means they will respond, you will get a transition, but transition is very slow. Okay, you will respond when your brother is going, very slowly you are moving your head, then you lift your body, then slowly you are walking. So that is called delay process, forbidden. First person, how first person? When mother shouted, very fastly, within seconds he was entered into kitchen room. Then that is called allowed. Remaining all are forbidden. Forbidden means don't think they are not responding. They are responding with not interest. So whichever transition not takes place with high intensity, whichever transition not takes place fastly, which is very slow, which is dead slow, which is not possible, that all are belongs to forbidden. Forbidden means many reasons are there. Forbidden means many possibilities are there. It may be slow, dead slow, not possible. That all are belongs to forbidden. Allowed means only first person. Whichever transition will give very fast response, that is called allowed. Whose absorption maximum is what? 10 to the power of 4. Whichever person respond fast, who can eat very high amount of food or not? He was responding very fast, so mother will give excellent food. They are not responding, so least priority. Here also same. So that's why try to respond for your mother. If you respond, you will get more absorption. Tasty food is available. First priority, more tasty food. When father comes, they will bring some fruits from outside. And that time you will respond very fastly or not. So if you respond very fastly, then absorption is very high. You will absorb your intake very high amount and excellent amount and good healthy amount. Suppose if you are not respond very fastly, what happens? If you are very slow in any, suppose if you go any function, suppose your absorption is very high, you are the first person supposed to enter into the function in dinner, eating. Suppose you are very slow, at last only white rice, one curry. Right or not? Will you eat white rice in any function? No, least priority. Right or not? It is also same. Forbidden nothing but you are eating but not interested. No other option, then only you are responding. That is a primary factor. That is called allowed. Now next is forbidden. It is all are related to UV only. If you understand this one, UV is dead easy for you. Only some selective mnemonics is sufficient. Then you can understand how lambda max is responsible to absorb by any chromophore. Next you write down low probable electronic transition in a molecule is forbidden. Low probable electron transition in a molecule is forbidden. Then the transition in a molecule takes slowly, very slow, or delay, not exist. Not exist. In UV visible range. With low intensity, UV visible range with low intensity or absence of intensity is forbidden. The transition in a molecule takes slowly, very slowly, or delay, or not exist. So in UV visible range with low intensity is forbidden transition. This is forbidden transition. Absorption maximum is less than 100 only. Whichever is most possible, allowed. Which is less, other than that, remaining all are forbidden. So only one allowed is there, remaining all are forbidden. Most probable transition which takes readily by absorbing UV visible range, that is called allowed. Intensity is very high. Here intensity is low, transition is very slow. Very slowly transition will take place. When transition is very slow, intensity of that band is very less. So generally carbonyl compound, how many transitions are possible? Carbonyl compound, 2 transitions are possible. These are the 2 possible transitions. This is lambda and this is absorption max. So this is one particular transition where you will expect pi to pi star. And here it is one more transition, that is n to pi star. 2 transitions are possible at 275 nanometers, here 178 nanometers. How many transitions possible for carbonyl? 2. Pi to pi star, n to pi star. These 2 already explained. Remaining total 6 possible, but only 2 are really exist. But what I am saying is, this is allowed, I am saying. This is allowed, and what about here? This is forbidden. whichever transition having more intensity, whichever transition having less intensity. So highly possible, less possible. More absorption, less absorption. Emax is very high. If you compare here, Emax is very high for this one. Emax is very high, but if you compare here, Emax is less. Absorption is very less, absorption is very high. More absorption allowed, less absorption forbidden. So in carbonyl compound, how many transitions are allowed? Only one. How many are forbidden? Only one. Which is a forbidden transition in carbonyl compound? N2 pi star. So that's why low intensity. Low intensity. Low intensity means height is very less. Absorption also very less. It will absorb this radiation very less. More absorption, if you are eating more amount of energy, more intensity. So you are getting your wavelength, but you are not eating clearly. Then your intensity is very less. Your favorite food is there, but you are not eating. Your favorite food is there, eating very high. So what is that? Favorite food 178. What is the favorite food? 275. What is the favorite food for N2 pi star? Food. N2 pi star. See, whenever your mother cook your favorite food, will you eat that in bulk amount or not? Will you eat or not? Or will you sacrifice your brother? No. Definitely you will keep at one place and you need to eat continuously. Because you need to satisfy. So whenever if you are continuously eating, then what? Your intensity is increases. So when favorite food is there, but you are showing negligency, then your brother will eat. So then finally you are not satisfied. Your intensity is very less and decreases. That is called forbidden. So when food is coinciding with your intensity, if wavelength is coincide for transition, on the time, if transition takes place fastly, you will get more intensity, that is allowed. Low intensity forbidden. Right. Clear? See, electronically excited state molecule, electronically excited state molecule with retaining spin and multiplicity. Retaining spin and multiplicity is allowed transition. It is allowed transition. Any electronically excited state molecule with retaining spin, spin retains anti-clockwise, anti-clockwise, clockwise, clockwise, and retaining their multiplicity is allowed. Okay, so inverting spin and multiplicity is forbidden. Multiplicity is forbidden transition. electronic excited molecule with retaining spin, clockwise to clockwise, anti-clockwise to anti-clockwise with same multiplicity, singlet to singlet, that is allowed. If it is singlet to triplet, not possible, clockwise to anti-clockwise, not possible. So I can say forbidden means singlet to triplet, allowed means singlet to singlet. So that is allowed and forbidden. Only two possibilities are allowed and forbidden. Retaining spin, retaining multiplicity, probable transition, most probable electronic transition with high intensities, all are allowed. So I can say this one, see here ground state S1 to this one, possible, S0 to S1. So what are they? They are allowed. Now even I can write T1 to T2 and T1 to T3, this is also allowed. Why? See, singlet singlet and here also triplet triplet, possible. Multiplicity retaining, singlet to singlet, SS TT, okay. But what happens, see, S0 to T1, possible, not possible, okay. Then followed by S1 to T1, possible, or S1 to T2, directly it is depends upon the gap, but most probably S0 to T1 is not possible. I can say this is forbidden. So I can write S1 to T1, this is called forbidden transition, forbidden, okay. Now I am writing a ground state molecule clockwise anti-clockwise and excited molecule, you focus on this one, ground state, excited state. Now you focus on this electron, only one electron you focus here. This is S0 state and this is S1 state. Is it allowed or forbidden? Ground state anti-clockwise, excited state anti-clockwise. Now it is, this is allowed. Remember, here I am writing ground state and here excited state, I am writing clockwise, clockwise. So I focus this one. Anti-clockwise, it is S0. Clockwise, clockwise, it is T1. Okay, anti-clockwise converted to clockwise. Is it possible? No. So now I can say it is forbidden. Forbidden, many meanings are there. Actual meaning of forbidden means maybe very slow, maybe not exist, dead slow. That is the meaning actually forbidden. So that is allowed and forbidden possibilities. Next, this is last one in case of electronic transition. Frank-Condon principle. Frank-Condon principle. So here see, time required for electronic transition. How much time required for electronic transition? 10 to the power of minus 15 seconds. 10 to the power of 15 seconds required. Now time required for vibration of atoms or bonds, that is 10 to the power of minus 13 seconds. Vibration of atoms nothing but bonds are vibrating. If atom vibrate means automatically bonds are vibrating. So sometimes in some books they will write vibration of bond they will give, otherwise you write vibration of atom, both are same. Means vibrating atom, electronic transition we are comparing. So indirectly which is having less time? Is it electronic transition less time or vibration of atom less time? Which is having less time? Electronic transition. Between these two which is high number? Minus 15 is high number or minus 13 is high number? Minus 13 is high number. Time is high, time is less. Within short time electronic transition takes place. So indirectly I am saying that before vibration of any bond there is electronic transition takes place. If you apply electronic transition suitable lambda. Okay, so here see, electronic transition is faster than, it is faster than vibration of bond. Vibration of bond. According to this principle, during electronic transition, position of nuclei and geometry of molecule unaffected. Position of molecule, geometry of nuclei is unaffected. So nuclear position never changes, geometry is unaffected. That is called Frank-Condon principle, simple principle. This principle is saying that when electron transition takes place, there is no effect of nuclei, nuclear position never shifted, and geometry is not affected. Only this is a key point. Geometry of molecule is unaffected in electronic transition. That is called Frank-Condon principle. Electronic transitions are faster than vibration of a bond. During that particular process, position of nuclei never changes, geometry of molecule is unaffected. At one particular lambda electronic transition takes place. Now see here two lines I am giving now. It is a line which is deviating. So this is a line which is exactly straight, E0 to E1. Now this straight line indicates that follow Frank-Condon principle. Okay, and what about here? This one. So it is not going to follow Frank-Condon principle. So generally this is not exist. This line what I am writing, this is not exist I am saying. Means if transition is very fast without any deviation, if transition is straight, exactly straight, means there is no geometry affected. But if transition little bit deviated, if it is changing their angle, transition is taking place but it is not exactly 90, it is slightly changing, means it is slow. If transition is slow, then geometry is affected. This is not possible, he was saying. So when electronic transition, this kind of transition not possible, he was saying. Always electronic transition straight and fast. So on that time there is no effect of geometry, no change in position of nuclei. Means ground state, exit state having same geometry. Suppose if I take a carbonyl compound, this is R and this is R. So here it is S0. Now, what is the geometry of this one? Trigonal, planar. What is the hybridization? sp2. Now after excitation, see, here R, this is R. Now it is excited. Now what about geometry still? Trigonal, planar only. This is S1 state. This is called Frank-Condon principle. Frank-Condon principle is saying that when molecule absorbs any light energy, it will be get excited. So whenever it is excited, the transition is very sharp and fast, and during that time geometry is unaffected. Position of nuclei also remains same. Position nuclei never changes. Suppose if it is changing, that is against to Frank-Condon principle, that is not exist, you are saying. Means if you are giving more time for transition, if you are giving more time for transition, on the time it will follow against to Frank-Condon principle. Okay, only one point you need to remember for Frank-Condon principle. During electronic transition, geometry of molecule unaffected, position of nuclei unaffected. Always electronic transition is faster than vibration of bonds. So that is about electronic transitions, types of electronic transition, multiplicity, Hund's rule of maximum multiplicity, what is allowed, forbidden, then followed by Frank-Condon principle. So next is Jablonski diagram. Jablonski diagram. Deactivation or de-excitation of electronically excited states of a molecule. So from this, from last year 2 times in CSR question is given from Jablonski diagram on. Very easy. De-excitation or deactivation. Electronically excited molecule. So this is actually meaning of Jablonski diagram. De-excitation, deactivation of electronically excited molecule. Means when molecule is excited, what happens? Whenever, if it is not giving any product, that is explained by Jablonski diagram. Okay, so Here see, this is a ground state, S0 state. It is taking light energy and it is excited. It is excited, that is S1 state. Okay, so or any excited state you can take, because it might be even triplet is also possible. Now it is coming back to ground state. Okay, now it is not giving any product. This is called de-excitation. So this line indicates that de-excitation. De-excitation or deactivation. So what is de-excitation or deactivation? See, returning of excited molecule, returning of excited molecule to ground state by releasing energy. By releasing energy is deactivation. Deactivation or de-excitation. Returning means it is coming back to ground state. Returning of any excited molecule to ground state by releasing energy or excess energy is nothing but deactivation or de-excitation. Okay, so de-excitation is a